Welcome to the 16th Geopolymer Camp. It is my pleasure to once again report on the latest developments in geopolymer research and development around the world. As it has become a tradition, I have carefully selected the most valuable results to highlight since the last Geopolymer Camp. I would like to draw your attention that since 2009, which was our first Geopolymer Camp, my presentations have been recorded and can be found on our Geopolymer Institute's website or on YouTube. You can view these videos for a more in-depth understanding of the evolution of geopolymer research over the years. I always start my keynote with the following pictures, because 90% of the participants are new. It is always interesting to show how it all began. The first Geopolymer conference was held in the University of Technology in Compiègne in 1988, located north of Paris. It is noteworthy that this conference took place 10 years after the discovery of the first geopolymer binder in our private laboratory, which was situated in Saint-Quentin here, near the present-day campus. 30 years later, the research, development, and applications of geopolymers can be found all over the world. Obviously, as the number of laboratories grows, so does the number of publications. In the first years, with my reference paper published in 1991, which is cited thousands of times, there are 1 to 3 publications per year, and then it starts rising slightly. In 2008, the Geopolymer Institute published the first and second editions of my reference book, Geopolymer Chemistry and Applications, and the 5th edition was introduced in 2020. This year's state of research and development comprises only one part. Usually I have 2, 3, or 4 parts. Today, only one. Geopolymer Science from primary to quaternary structures. In 1976, when I first introduced the concept of mineral polymer, which 2 years later became the generic term geopolymer, the mainstream of scientists could not imagine that polymers existed outside the well-plowed field of organic polymers. We have presently 2 systems: polysialate alkaline-based geopolymer, sodium-based or potassium-based, and alumoxy-acid-based geopolymer, phosphoric-based and organic acid-based. First, polysialate-based geopolymerization. We know that the geopolymerization mechanism of the alkali polysialate-based geopolymers includes 6 steps. Those who attended the tutorial yesterday learned about the connection between these steps and the process methodology. The 6 steps are alkalination, depolymerization of silicates, gel formation of oligosilates, polycondensation, reticulation networking, geopolymer solidification. In addition to the chemical mechanism, some physical parameters are also very important. Geopolymers have a specific 3D shape and are organized into different formations or structures. From primary to quaternary structures. There are 4 levels of geopolymer structures which are related to the chemical mechanism. First, alkalination and depolymerization of silicates is the primary structure. The gel formation of oligosilates is the secondary structure. The polycondensation is the tertiary structure, and the reticulation, networking, and the geopolymer solidification is the quaternary structure. This is what I learned when I studied organic polymer chemistry 60 years ago, and I have transferred all this knowledge from the organic to the geopolymer. Primary structure refers to the atomic composition and chemical structure of the monomers obtained during the alkalination and depolymerization of silicates and aluminosilicates. The primary structure of alkaline sialate geopolymer refers to the soluble monomeric unit of molecules. Among the potassium-based monomers, 5 soluble molecules were discovered, namely number 1, orthosilate, SiOAl, number 2, orthosilate disiloxo, 1 SiOAl and a siloxo attached to the silate, number 3, orthosilate disiloxo, but here no longer linear but on a triangle, number 4, orthosilate disiloxo, and the squared structure, which is very important essentially for sodium-based geopolymer, the orthosilate disiloxo, which has SiOAl and 2 SiOH. You can find all these structures in my book, chapter 6. The next level of geopolymer structure corresponding to the chemical reaction, gel formation of potassium oligosilate siloxo, is the secondary structure. It refers to the formation of the oligomer with hexagonal shape through the chemical reaction of the monomer potassium. This is valid for potassium. The potassium orthosilate structure and reaction with potassium silicate. So we have SiOAl and 2 SiOAl, which react with 2 silicates molecules. And we get the first hexagonal secondary structure. The next step, polycondensation, produces a 3-dimensional ribbon. It is called the tertiary structure. The tertiary structure is primarily due to the chemical reaction between the hexagonal shape oligomers, the oligosilate of the secondary structure, and one gets an hexagonal, each hexagonal unit reacts with another and producing a 3D ribbon. This is valid for potassium. The overall 3-dimensional structure of geopolymer is called its quaternary structure. The quaternary structure is primarily due to chemical interaction between several ribbon structures of the tertiary structure, yielding a 3D network or framework like the leucite framework, the natural geological material leucite. Several geopolymer laboratories, including our geopolymer laboratory here in Saint-Quentin, have discovered this quaternary structure under the electron microscope. In 2003, Waltraud Kriven and her team at the University of Illinois in the USA investigated with the transmission electron microscopy the macrostructure of fully reacted potassium sialate siloxo type geopolymers. The geopolymer was the result of a salt-gel reaction. They found that it consists of individual nanoparticulates ranging from 10 to 20 nanometers in diameter. They are shown on the slides or at the pointed tip of the arrow. The scale is 500 nanometers and the subscale is 50 nanometers. It is the accumulation of these nanoparticulates or individual particulates that forms the geopolymer matrix. I refer to these particles as geopolymer micelle. They have the same dimensions as organic polymers. So presently, today, the geopolymer chemistry and structures and some organic polymers are similar. 9 years later, Dong-Kyun Seo and his team from Arizona State University in the USA conducted a study with a regular metakaolin-based geopolymer produced under high aqueous dilution. The scale is 20 nanometers. During the reticulation process, the geopolymer micelles, which are 10 nanometers in size, were clearly visible under the transmission microscope. This has been a presentation of, at the Geopolymer Camp 2018, and you'll find this presentation on the Institute website. The geopolymer matrix is made of nano and submicron ellipsoidal particulates, which we call geopolymer micelles. The figure shows the very small dimensions of the geopolymer nanoparticulates, geopolymer micelle, when compared to other spherical structures like colloidal silicae, silica fume, or fly ash. Geopolymer is a nanomaterial, a polymer. It is not a gel. The starting metakaolin in the Arizona State University experiment was the commercial product Metamax, with its typical tabular macrostructure for metakaolin. The scale is, the subscale is 200 nanometers. Last year, I mentioned in my keynote 2023 that our geopolymer laboratory here had started a 3-year project to develop direct ink writing, 3D printing of high-strength, stable ceramic-type geopolymers. During this study, we came across a series of metakaolins which have very high strength. In the literature, the mainstream, the flexural strength is around 10 MPa. In our geopolymer lab, with all-purpose commercial metakaolin, like the Metamax, the value is around 15 MPa, flexural strength. The new metakaolins have a flexural strength in the range of 25 to 30 megapascal, and a compressive strength of 180 MPa with the same mineral filler feldspar in all trials. They are well suited for the 3D printing of ceramic-like geopolymer products. The raw materials are these geological materials that are called kaolin clay. Under the scanning electron microscope, the subscale is 200 nanometers. We discovered that these raw materials are a naturally occurring mixture of kaolinite with its large crystals and halloysite. But this halloysite is not like the well-crystallized rigid nanotubes Here we have unfolded nanosheets or nanoplates. This structure was published in 2019 in a paper titled Characterization of Diatomate Earth and Halloysite Resources of Poland by a team from the Silesian University of Technology. The halloysite nanoplates are well distributed throughout the samples, and their shape is different from the nanotubes normally associated with the mineral halloysite. After calcination at 700-800 degrees C, the resulting metakaolin is a naturally occurring mixture of metakaolinite and metahalloysite. Another high-strength metakaolin comprises also metakaolinite and metahalloysite. The subscale is 200 nanometers. These high-strength metakaolins are used to manufacture high-strength 3D-printed geopolymer ceramics. High-strength 3D-printed geopolymer ceramic, 0.7 millimeters to 1 millimeter thread, chemically stable, potassium-based geopolymer with high-strength metakaolin 750 and feldspar filler. That's all. Compare the size with the €1 coin that is on the left of the picture. We took one of these new commercial metakaolin as received from the supplier to make a potassium-based polysialate siloxo geopolymer item. Under the scanning electron microscope, with very high resolution, the subscale is 100 nanometers, the matrix of the potassium-based polysialate siloxo geopolymer is made of individual geopolymer micelles, identical to the previous ones, but we see also intact very thin hexagonal crystals of metakaolinite embedded in a geopolymer matrix with nano geopolymer micelles. In other words, the geopolymerization was not complete. After grinding for 10 minutes the liquid geopolymer resin containing potassium silicate and the metakaolin, the matrix no longer shows unreacted metakaolin, only geopolymer micelles. After 20 minutes of grinding, the quaternary structure of the geopolymer micelle is well defined and essentially here, and the expanded view displays beautiful individual geopolymer micelles with overall dimension in the range of 10 to 20 nanometers. The conclusion of this study is that we have demonstrated that the quaternary structure of metakaolin-based geopolymer is a well-defined 3D polymeric network in the form of individual particles called geopolymer micelles, with overall dimension in the range of 10 to 20 nano. The quaternary structure of the nano-sized potassium-based geopolymer micelle retains the same shape when heated up to 1000 degrees C. Its microstructure also remains X-ray amorphous. At higher temperatures, it crystallizes into the mineral leucite with a melting point above 1400 degrees C. This is a potassium-based geopolymer, not the sodium. The sodiums will provide a different structure, but also the geopolymer micelles. This explains its unique structural properties. For example, excellent thermal shock resistance at high or very low temperatures, resistance to high vacuum, making it the ideal material for lunar, space, and extraterrestrial applications. Cement scientists who promote the misconception that the result of geopolymerization is an ash or cash-type hydrate are mistaken. Alkali-activated materials are not geopolymers. This has been explained in different articles and videos that we posted on the web entitled Why Alkali-Activated Materials Are Not Geopolymers. These cement scientists can purchase the Geopolymer bundled book and learn how to produce true geopolymers. The second geopolymeric system is the Alumoxy-based Geopolymerization that we call ALOX. It uses an acidic medium, either phosphoric acid-based or organic acids-based. With metakaolin, metakaolin is always reacting with these acids. The geopolymerization mechanism of the alumoxy-based geopolymers is different from the alkaline-based. It starts with the decomposition of the aluminosilicates into two units. First, SiO2. We know that metakaolin, when added to acid, the acid extracts the SiO2. First, SiO2 units. Second, alumoxy units. For example, with phosphoric acid, and we get the phosphate-based geopolymer that is explained in the chapter 14. For organic acid, we don't have anything written so far. For phosphoric acid, for example, phosphoric acid reacts with metakaolin according to the chemical reaction H3PO4, phosphoric acid, metakaolin yields SiO2 and aluminum phosphate. Under the electron microscope, we see the two different geopolymeric networks. The first geopolymeric network on the left is based on SiO2 units. And the second, it is the one in dark gray. In light gray, we have the second geopolymeric network based on aluminum oxide phosphate. This aluminum phosphate geopolymer has a very special three-dimensional quaternary structure, namely that of quartz. Aluminum phosphate is the beryllinite, which is isostructural to quartz. It has the same structure, that is, the helical structure, which is isostructural to quartz. This explains why the X-ray diagrams of the alumoxy geopolymer aluminophosphate are identical to the X-ray diagrams of SiO2. Same for the high temperature quaternary structures aluminum phosphate tridymite and aluminum phosphate cristobalite. Instead of SiO, SiO, SiO units, we have ALOP units, but they are identical. So this structure is very, very stable. The second Alumoxy geopolymer reaction is based on organic acids. We believe we have now found the principles of the Alumoxy-based Geopolymerization ALOX. They are no longer alkaline-based sodium, potassium, SiOAl, sodium, potassium silate. It was not easy. We had to take a new approach. But thanks to the perseverance of my son, Ralph Davidovits, we succeeded. One of our breakthroughs is the ability to replicate ancient artifacts such as the hard stone vases from the early dynasties, 2500 BC in Egypt. These vases are thought to have been made from geological hard stones, an impossible carving task indeed. We believe that these ancient artifacts were made using artificial stones. I have always maintained that these vases were made of a moldable stone paste similar to clay and ceramics. Indeed, they were made using a method very similar to that developed at Pumapunku, Tiwanaku in Bolivia, South America, for the andesite volcanic monuments. See the articles and videos at the Geopolymer Institute website at www.geopolymer.org archaeology. And my book, Ancient Geopolymers and in South America and Easter Island, will be published by the renowned publisher Springer Nature this November 24. We have here some samples of this material. It is ceramic and it is impossible to break. This has been my state of the geopolymer research and development for 2024. Thank you for your attention.